that much time. So this is a paper about fuel, which is a work that we are doing together with Martin. Martin is a student from Argentina, and he came to France for implementing his thesis. So we work together on fuel. Apart from that, Martin is being sponsored by ISU through the project of Summer Talk, and I'm being his mentor. So thanks to ISU for sponsoring this project. Sorry in advance if some of the parts are too basic for you or too low level details, so I always try to make most of the audience get as much as possible. So forgive me if. So the idea is that we have a normal object, like a point, for example, when we finally have object point to other objects by references, so at the end what we usually have, it's a graph. So when we talk about serializer and I will serialize an object, what you usually have to deal with and what you serialize is a graph that is behind that object. So that's what I like to call fuel an object graph serializer, because that's what all serializer does. It's not just fuel. So the basic idea of a serializer is you take as an input an object graph, which is an object, suppose I take a point, and as a result you want a chunk of bytes. That's serialization. That's as simple as it could be. And the opposite process is the materialization or deserialization. In fuel we call it materialization, and this where the input is a stream of bytes, and you want to get back the original object graph, which in this case was the point. That's the basic step of serialization and materialization. Once we have serialized an object graph and when we have the stream of bytes, we can do that whatever we want. For example, we can put it in a database, we can store it in a disk, keep it in memory to do something else, we can store it in a NoSQL database, we can send it through the network to do, for example, in a web application, you can serialize things, put it in a session, in request, or something like that. So, serializers are used very widely in so many scenarios. Fuel started with several goals in mind. It was started from scratch after failing to find a good serializer for Faro. So we are not doing this for fun because we need it. And the idea is that these main goals are already done, so they are characteristic as well as main goals, but we want to do focus that we will continue to have those goals. The idea is to be fast. I mean, our purpose is to be fast serializer because some other serializers focus on portability, for example, as SRP, which is another common serializer, but in our case, the speed. And mostly, the serialization speed of materialization. And I will explain later why. The idea that we can build it from scratch with good object-oriented design, so we can make it easy to extend and to understand for every normal person. We don't want to depend on the VM at all, because, for example, in assignment depends on to be primitives implemented in the VM side, so it's quite complicated to maintain and to change. And finally, we want to really split the functionality between the serializer and the build and the tools that are built on top of it. For example, parsers, it's a really good serializer, but it's very, very coupled with the code management of Visual Works. So, for example, there's a problem if you know that parser, what you do with the code and the source code, etc., etc. In our case, Fuel is just the serializer, and then you can build tools on top of it. So the key features that most serializers do more or less the same. In the case, okay, I told you we have fast serialization and materialization. Then we support the famous class shape, that is, you serialize an object, and while it is serialized, the class of that object has changed. It adds an instance variable, or you remove, or you rename, or things like that. So when you materialize, you need to update those instances. So we support the automatic, because sometimes there is need of a manual iteration to fix and migrate the version, but if it's possible, we fix it automatically. This is very important for us because we really want to be able to serialize whatever. We serialize context, closures. We can serialize classes completely with the meta classes and compiling method and things like that. So that's one of our focus. In contrast with other serializers which do not care to serialize a context, for example. The other is, of course, the text cycles. We also support global references. So, for example, if you have a graph and you have a pointer to a transcript, for example, it is not completely serialized the transcript, but instead you just store the global. So when you materialize in an image, you won't duplicate the transcript. This is very important for the serialization part, is that we have a buffer writing. So we have a buffer write string where we have a small buffer and we flash every time it is full. So we go to this very few times. And of course, all serializers, because it needs to support some hook methods. For example, the user may need to declare some instance variable as transient, or some object need to be replaced by another one, and things like that. So the idea is to support dot hooks method that usually users need. And the key characteristics of Fuel is this one: is that the binary format of Fuel, because Fuel is a binary serializer, and what is most important is that it uses what is called a picker format. So far, the only picker format I have seen in Smalltalk is parcels. So Fuel start looking by parcels.
What is a picker format?
I will explain it now. The other of the key features that are related to the picker format, but we will see that basically we can group objects in what we call clusters. I will explain later. As we have to do an analysis phase before the writing, where we explain them all together now. Okay, that's fine for the moment. So what is the picker format? And this is the key point. The idea is that we want to spend a little more time during serialization in order to encode the object in a way that the materialization process is much faster. That's what we do with the picker format. Even though we demonstrate that with our benchmarks we are even fast in serialization, where we should be slower. But with some techniques we are fast as well. So the idea is that we group objects together. That is that when they are serialized one after the other one. The most common case is that cluster is the type of an object, its class. So for example, if you have the class person, all the instances of person will be all together. But that's not the only example. For example, there are a specific cluster for nil, true, false, or a specific cluster for byte arrays, or a specific cluster for float, or things like that. And we will see an example. I was trying to do a metaphor to explain this, so maybe it's a little stupid, but I think it's worth it to do the metaphor. So imagine that we have a lot of shards, and each shard contains stuff inside. So you see, each shard has a specific type of element. You see, each of element is not in another shard. So one shard only has one specific type of element. The shards are in order, one next to the other one. They are not just all mixed. Each shard has a label where we put what you have inside and how much you have inside. And finally, each shard can have different sizes and different amount of elements inside. So, if we replace shard by cluster, it is the same. This is what we do. So basically, what we do is that for each cluster, we have a specific type of object. Okay? For each cluster are in order. So it can one cluster, then the next one, and the next one in the string. Yes?
Specific type of objects.
Yes.
Class?
Not necessarily. It is the cluster, in fact. So most of the times, an object is associated to a class, because a class is for a cluster. I will show you an example now. But imagine that a cluster can be to group, for example, all nil, true, and false. That can be one cluster. And another one can be just grouping instances of user. Okay? And the same happens with the label. So each cluster will have a label, which in our case will have an ID. And we also encode how many elements are inside that cluster. And of course, each cluster has different amount of objects inside. So to answer Alexander's question, the idea that we can have one cluster. So, for example, So what we do is we serialize the ID and then all the information from that cluster. So in our case, for each cluster, we store, for example, the class name of the cluster, the amount of instances that follow the cluster. And in fact, there is more information, but I want to minimize it for the example. And then we follow to the next cluster, and the next cluster, and the next cluster, and like that. So why we want to do that? Why this is better than regular serializers? In a regular serializer, when you serialize a graph, it iterates the graph, it traverses the graph, and the objects are written in the stream while the graph is being serialized. So when you materialize, you need to materialize the same way. You start to materialize, you read one object, you fetch the type, you see which class it is, then you say basic new or whatever to recreate the object. Then you know that the following two are two references, so you create those and like that. So you recreate the graph like traversing, like retraversing again. With the bigger format, what we can do is that since objects are grouped in clusters, we read, for example, the first cluster, and we know that all the following objects are from the same cluster. So we can just loop and recreate the objects in an iterative way instead of traversing the graph. So the key point is that with the standard serializer, we have the recursive materialization for the graph. In the contrary, with Fury, we can do it iterative. So we just loop and recreate the object, and then we fix the references. And that is much faster than having to materialize the graph in the way it was serialized. So the advantages of this is that, as I told you, we can do what we call bulk materialization. So we just read the clusters. Say that we read the cluster for user. So we know that all the 200 following objects are user. So we do user basic new 200 times, and we already know how many times we have to create. And that's efficient as well because we only store the type of an object only once in the stream. Because all serializer has to store the type next to every object. Because you don't know the type of the object. You need to store the type so then you can, from the type, get the class and do the basic new, or however you recreate the object. This way we only store it once because we know that all the following objects are from that type. Another thing is that we store the sizes of everything. So for example, we store the amount of clusters, we store the amount of instances inside each cluster. We can do all loops from 1 to n, do. So we know in advance all the sizes. It's extremely fast to loop. And of course, the generated stream is smaller because we don't encode the types for every object. We encode it only once. So this is important when you are sending the stream by a network, for example, where the size of the stream is important. But however, of course, there are drawbacks with this, and it is in a normal serialization, you just have your object and you just put them together while you serialize the graph. But in our case, we need to group them in these shards, in these clusters. So we need to do what we call analysis phase, that we need to first traverse the graph and associate each object with a cluster. And that's the extra overhead that we have in serialization. So we need to first traverse the object graph and we map object to a specific cluster. This is what we call the analysis. So basically, we take the graph and we have a visitor where each object can answer each cluster. So at the end, what we have is a dictionary where each key is a cluster, and then the value a list of the instances of that cluster. So once we have that, we go to the serialization step, and this basically we take that dictionary and we iterate, and for every cluster we say, okay, cluster, serialize all your instances, and each cluster implements those two methods, serialize and materialize from. So each cluster defines the way that objects are serialized and materialized. So if you want to extend or optimize or change, you can subclass and change it. Another improvement that we do is to use a stack over a recursion, because usually when Serializer traverse the graph, they do a recursion. So you read one object, then to serialize its references, you get the references and you call again the same method. So that's a recursion. In our case, we put the objects in a stack. So we don't use a really large stack, and that it's performant from the point of view of the GC, and we don't need to keep all the stacks alive, and it's faster. So the basic steps for serializing is you do the analysis first, and then you just serialize the header. And this is important because we have to first serialize the instances, and then we serialize the references. It's a little bit complicated to explain why, but basically what we do is in the stream, we serialize the instances. Just no references, the object we write. And then following, we write the references which are offset inside the same stream. Because then after, during the materialization, we will do a loop to materialize all those objects, and then we fix the references. That's why we can do that because of the pickle format. Because in a regular object serializer, you don't have that problem, because you are reading the object in the order that you need to recreate them. But that is slow. So, Fuel has been used for the moment for Moose to export the models and to import them back. We did an integration with Samsung DB, so instead of DB, so now with Samsung DB you can serialize using Fuel instead of a reference stream, and it works and it speeds up quite a lot. We know someone did a peer persistency strategy that uses Fuel instead of the image persistency, so that works out of the box. I tested, and we also did some export and import of peer kernels, but it's difficult to automatically set it inside C-side, because you need to set it inside an application. So the export and import works well, but then it gets complicated. Fuel was supported to speed, LMIN supported in 2 days. We use it for NoSQL databases, because NoSQL databases usually receive a binary, so we can serialize, get a binary representation, then serialize it to a no database. And from Area, which is my own project, but I don't because I have time. So the future work is to continue with optimizations. We want to create a tool that can load classes and to manage code in order to replace maybe multi-chiller in the future. But that requires a tool on top of Fuel. Partial loading of a graph, which is interesting when you want to just materialize a part of the graph. And okay, the rest of that is important. So from the benchmarks, we can see that for memory-based stream, we are not the fastest ones, but maybe the third. We compare with Storm, Magma, Smart Reference Stream, in a segment, SRP and Fuel, all the one we could test in Faro, because if you compare different virtual machines, it's very difficult to get real. And if you see in 5 basic streams, which is most of the time what you use, Fuel is extremely fast, even during serialization. So we are even fast in serialization, which is not our focus. The difference between both of them, because we do the buffer write stream. For materialization, we are for
Can you go back?
Yes. Oops.
Just there. So, should it be small or large?
Sorry?
Small is better.
Sorry?
Small is better.
Small is better. The left are the Y are the tests that we serialize. For example, in Kevin, we serialize bitmap, bitrise, charges, blah, blah, blah. And this is the time spent during the serialization. So the smaller, the better. It's difficult to appreciate this from the slide, but then if you don't know it and you watch it, you can see it better. So finally, for file-based stream or network stream or whatever, we are fast during serialization. For materialization, we are fast, no matter which stream. That's because of the bigger format. If you can see, we're much faster. For non-primitive objects, it's the same. If you take large graph of things, we are more or less have the same results. So this is the links. We have the website, the Schwager, the storage repository, and the Hudson. But in the Hudson, it's not very stressful, because sometimes you don't understand what is happening. So So here is the explanation, and it's always well. But we like to do TDD, so if you go and you see that the Houston is red, it's because we are doing TDD, so don't worry, but you can just go to Houston. So the conclusion is that, our conclusion is that if you really take care to do a good design and a good binary format, you don't need the VM at all. You can do a very fast serializer and with good design, and you don't need the VM at all. And your conclusion should be that here is a vehicle in the infrastructure. It just serialize and materialize. And then on top of that is where you should build your own tools, do stuff with that, like this one. So that's all. Okay.
We have time for one short question.
Mariano, réplica de phase K. C'est Q de phase K?
Okay, yes, better. It's a fast car.
Ah, ici de phase K, ok.
Yeah.
What do you have, like a cluster? What do you have an ID if you already have the class name?
Good question. In fact, in the last version, it is the class name and not the ID. Because with ID was easier because we don't need to deal with class renames. But the fact is that storing ID is complicated because if you then create new clusters, you need to all the time be sure that you are not using the same ID. And so now we just serialize the cluster for each cluster. I prepare an example for the slide, where there are nice graphs explaining step by step the serialization and materialization. Of course, I know I didn't have time for that, but if someone wants to watch it, I can do it. I will be here. So that explains in real how it works.
You said that you can serialize any kind of object. I'm wondering whether you can serialize even a process.
Yes,
you transfer to another image and then just receive it and it works.
Well, yesterday in the awards I serialized a whole debugger and I materialized it in another image and I continue the debugging. So you can serialize most of the stuff, but the fuel responsibility is to serialize and materialize them. It's not its responsibility to make sure that you have a completeness representation of the object when it is materialized. So for example, if you give me a socket, I serialize it and I materialize it. Does it work when you materialize? I don't know, if you load it in another operating system, it won't work. Because the socket represents a socket open in your environment. Or a process, for example. If I materialize a process, I will materialize the process, but I don't put it back in the scheduler process queue. Or whatever, I don't do resume.
I suggest we continue the discussion offline. Okay, thank you again. The next talk is